All right, let's take a look at an example of one of these problems. So we have 253 grams of some kind of unknown metal is heated to 54 degrees Celsius, then quickly transferred to a calorimeter with 75 grams of water at 25 degrees Celsius. The final temperature of the water plus the metal was 37.2 degrees Celsius. Identify the metal by determining its specific heat capacity. So again, this is a pretty similar plug and chug type of question. We know that all the heat that the metal loses will be absorbed by the water. So these two values will be equal but opposite. And then, of course, we know that Q is going to be our MC delta T, where delta T is this TF minus TI. And so then we can write a bigger equation, and we can just use subscripts to identify what's talking about the metal and what's talking about the water. Right, so the mass of the metal times the specific heat of the metal times the final temperature of the metal minus the initial temperature of the metal is going to be equal to the mass of the water times the specific heat of the water times the final temperature of the water minus the initial temperature of the water, right? So you can see keeping track of where all these units are and keeping organized is going to be an important part. So the question says to identify the metal by determining its specific heat capacity. So we want to identify the specific heat capacity of the metal. That's our CM right here. So we want to reorganize our equation. We're going to divide both sides by negative m times negative mass of the metal times the delta T. So we'll end up with CM is equal to negative mass of the water, specific heat of the water, and then the temperature change of the water divided by the mass of the metal times the change in temperature of the metal. And then we simply just go through our problem and find out all of our values, right? We have 253 grams of the metal, so that'll get plugged into there. It's heated up to 54 degrees Celsius. That'll actually be the initial temperature of the metal, right? That'll be before we drop it into the water and it cools back down. We see that the calorimeter has 75 grams of water, so that'll be the mass of our water. We see that that water initially starts out at 25 degrees Celsius, so that'll go into there. We, of course, know the specific heat of water from our table here, 4.184 joules per degree Celsius. So that'll go into the specific heat of the water. And then finally, we're told that at the end, they'll reach thermal equilibrium, which is almost always true, right? So our TFs will almost always be the same value. And in this case, they're both 37.2 degrees Celsius. So those will be your values right there. Of course, you want to be careful of units as well, but in this case, I think we're pretty good. So we'll have negative 75.0 grams of water times 4.184 joules per gram degree Celsius times 37.2 degrees Celsius minus 25 degrees Celsius divided by the mass of the metal, which was our 253 grams. And then minus the final temperature, which was 37.2 degrees Celsius, minus 54.0 degrees Celsius, right? So the metal got cooler than it initially was. Then if you think about the units, all the canceling works out pretty well. This gram can go ahead and cancel out with this gram. These Celsiuses will all cancel out with one another. Oh, it's not that gram. Cancel out with this gram right here, and then we'll be left with the joules per gram degree Celsius, which is exactly the correct units. So our specific heat of the metal, if we type that into our calculator correctly, hopefully we'll get 0.901 joules per gram degree Celsius. If then we take a look at our table and try to match it to the correct metal, we see that it's most likely aluminum. So again, just take a look at some practice. A big part of it is just recognizing which equation you need and then using algebra to manipulate the equation. And then, of course, reading your word problem and picking out which pieces of information are useful. Maybe you'll have some distracting information that isn't used, that kind of thing. A key thing with all of these calculations is that we assume no heat is lost to the environment. That's probably not true in real life, but it just depends on the quality of your equipment and your experiment.